So before today, when we were talking about continuity, we were really just talking about being able to trace a graph. So just real quick, looking down at this A, B, and C, if you were to trace these, you would have to pick up your pen or pencil. Okay, that is not a good enough explanation. We are never going to write that down. AP graders are not going to like that, and neither am I. But it's a way to kind of help you understand, just real basic right off the bat, is this thing continuous or not? When we talk about continuity and we start getting into a proof, I don't want you to think of trig proofs. Okay, there's lots of different types of proofs, but proof is the best way I can explain it, because you have to talk about these three conditions if you want to talk about continuity at a point. You have to show these three things. It's not really that difficult, and it's the same thing each time. So in that regard, it's really not like proofs you've had before. So the first thing we have to show is that the limit exists at that particular point. And so, like, if we have two sides, we have to show that the left side is equaling the right side. We just practiced left and right-sided limits, so this is something we're going to continue to practice today, but that's why we did that before this lesson. The second thing we're going to do is show that there's an actual point. Okay? When we're talking about continuity, having a limit's great, but there also has to be a real point, not a hole, but an actual point. And then the third thing is that whatever you get for the limit has to equal whatever you get for the point. So when we're doing these calculations, if we say the limit equals 5, and then we say f of a equals 5, we're going to have to show that those two things are equal. And if all of these things are true, we have continuity. If any of them are not true, we have discontinuity, and that's how you prove it. Okay, so before we really practice an example, I want to show you why these three conditions might break down. So looking at A here, does the limit as x approaches c exist? Yeah, the limit exists, so I'm going to put a check next to 1. Okay, does the point exist when x equals c? Is there an actual point? No, there's a hole, which is the opposite of a point. So 2 is where that breaks down. So it's like an x, like a no, condition 2 is not met. All right, what about for B? We start back over with 1. Is the left and right-sided limits the same or different? They're different. So guess what? The limit doesn't exist. Condition number 1 was not met. What about C? Does the limit exist? Yes. Check. Does the point exist? Yes. Are they the same? No. So that's graphically where the conditions can break down. So let's get into an actual example, one that you're going to need to be able to do. So we have to show these three conditions, and I am going to make this a little thinner so I can write more. All right, so we're going to start with condition number 1. That means if there is a piecewise function like this, we need to do the left and right-sided limits, which is what we practiced yesterday. So I'm going to start with finding the limit as x approaches 1, because that's what they're telling me to look at, from the left side. Which piece is the left-sided limit going to be? The cubic or the linear? Why? Yeah, because of that less than. So then we're going to show that we're plugging it into the cubic. We're going to show that we're actually plugging in the 1, and we're going to write 2. The left-sided limit is 2. Now we're going to find the right-sided limit, which is the other piece. And so again, 1 plus 1, hey, that also equals 2. So when these two things are the same, that is the limit. So we got to write it one more time. And we can just write f of x here to show that we're talking about the whole function. That equals 2, and for good measure, I'm going to say exists. Because that's really what we're trying to do on condition 1, is prove that the limit exists. But saying it equals 2 is good. It's going to help me in a future step if I go ahead and list that. Okay, condition 1 is the most work. Condition 2 is really not that bad. Okay, I'm going to kind of do like this so that I can see that this is separate. So condition 2 is going to be f of 1. Now, which of these two pieces is f of 1 going to be determined from? Whoops, sorry guys. There we go. The second one, because of the or equal to, right? So again, we're going to show the 1 plus 1 and that it equals 2. I'm kind of encroaching on example 2 space. So we'll do something like that. And again, let's just go ahead and write exists for good measure. Because that's what condition number 2 is really saying was, does f of 1 exist? Now, because I've already said that the limit equals 2, and now I've said that f of 1 equals 2, I can just simply say, state it. And this may seem redundant. You may be thinking, why do we really have to write this down? Well, it's the third condition. We're not really proving that this is true, but we're stating it, and you have to state it. This is a really picky College Board thing. All right, now you got to put some kind of transition word here. So thus, what does this symbol mean? Therefore. You feel free to use the symbol, or feel free to write the word so, or thus, or therefore, or whatever. College Board wants to see your 3 conditions met, and they want to see a summary statement. F of x is continuous. That's an appropriate abbreviation. At x equals 1. That's what they were asking us to show, or asking us what is it, and it's implied that we have to prove it. Again, it's not like you want to write all this down, but it really isn't that hard. Okay, most students miss points here because they try to shortcut and they like to skip to the end. You've got to show those steps. Okay, so let's do example 2. All right, so first condition. We're not really, we're not really doing left and right sided limits, okay, because this isn't a piecewise function. So we're just going to do the limit. So the limit as x approaches 2 of x squared minus 7x plus 10 over x minus 2. And this goes back to what we've been doing for a few days now. Plug it in. 2 squared minus 7 times 2 plus 10 over 2 minus 2, and that equals 0 over 0. And I'm going through the number crunching part fast because I'd rather just spend more time explaining the concept. What does 0 over 0 mean? Do more. So that, in this case, means factoring. So that's going to be x minus 2, x minus 5, which cancels those out, and then 2 minus 5 is negative 3. Okay, so that limit exists. Condition 1 is met. Now we try condition 2. It's always show that the limit exists and what it is, and now we're going to show that f of 2 exists. Okay, f of 2 is what you get when you actually plug 2 in. Now we have already shown the work to show what happens here, so we're just going to write 0 over 0. You could show that work again, but if it's already shown, then that's good. If you're ever like, should I show this or not? Just show it. And when we're doing limits, we're going to do more here, but when we're doing points, what does this graphically represent? A hole, which is not a point. Okay, we could say undefined, we could say that this point doesn't exist, and we get to stop here. We don't have to do condition 3. If condition 1 or 2 is not met, then you stop and you just say, therefore f of x is not continuous. So the not continuous examples are actually easier. You do less work because you get to stop as soon as you find one's not true. Okay, so that's what I mean by a proof. Every time you got to show the 3 conditions and you got to write a summary statement. Okay, so look at this next example 3. This is an old AP test question, not really that old, but was on the AP test a few years ago. And it says let F, and then look, there's trig and an E, but don't let that throw you. It's going to be fine. And then this says show that F is continuous. What is that implying? That all 3 conditions should be met. They're not asking us if F is continuous. They're saying it should be. So if you get stuck along the way, let it guide you that all 3 conditions should be met. So let's start again, and this is a piecewise, so we're going to have to do the left and right-sided limits. So the piece for the left side always is from this x less than, which is typically the top, but not always. You're really looking at the less than. And so 1 minus 2 sine x. So that's going to be 1 minus 2 sine of 0. And does anybody remember what sine of 0 is? Okay, so some of you are right and some of you are wrong. What I'm going to do is just pretend like I don't know for a moment, and let's do the next one. We'll come back to it. Okay, so let's do the right-sided limit, which would be this other piece for the greater than part. And here we get e to the 0. Now this you should know. What's a number to the 0 power? 1. That's 1. So what should this up here totally be? 1, which means that sine of 0 is how much? 0. Okay, but I hate to even put this on a recording, but you can kind of BS your way through this. You know that these two should be the same, so just write an equals 1. If you're not comfortable with it, it's okay. All right, you'd get full credit for that because you really can't tell that what you don't know. So if both left and right-sided limits equal 1, okay, and again, I know that these two things, this has to work because of the phrasing, right? It's not that everything's continuous. It's the way they stated that. It wasn't even a question. It was like, do this. Okay, so we know that then the limit equals 1 since both the left and right side were 1. All right, so that's the first condition. Okay, second condition would be find f of 0. And again, you just look for the piece with the or equal to, show that you know what you're doing. You know it has to equal 1 because you know all 3 conditions have to be met because of the phrasing of this statement here. You still got to show it though. I mean, that's what you're getting credit for here. You're not getting any credit for finding out that it's continuous. You're getting credit for showing that it's continuous. We really should be writing exists. I'm kind of getting carried away here. You would get credit without writing that, but I think it's a good measure. In case you mess up on the number, but you write exists, I think you could get points that you otherwise wouldn't get. Therefore, f of x is continuous at x equals 0. Don't leave off at x equals 0. That's important. This thing may not be continuous everywhere. I'm not asking if it is. Just add x equals 0. Okay, so let's look at the next page. I'll give those of you time to finish copying this. And I want everybody who's done copying, I want you to look at 4 and think about what that graph looks like. Okay, first of all, the parent function here is natural log. The absolute value bars may be throwing you off. Okay, let me explain something. This is what just plain natural log looks like. I'm about to erase this, so if you want to list it or if you want to draw it in your paper, you can. All right, now, do you see how the domain here is only positive numbers? That's because you can only take natural log of positive numbers. How do you make something positive? Absolute value. Now, you may be thinking, what about that absolute value transformation? Okay, we could get so far deep into this problem, it's not even funny. But when you see this, we're just not going to deal with those absolute value bars. We're going to say they're there because we're taking natural log of something, and you can only take log of positive numbers. Okay, so what's the transformation on this one? Right to. Why not down?
It's not outside.
Y'all all know that one. It's not outside. So there we go. That's what that graph looks like. Now I'm going to show you in a second how to do this if you didn't know how to graph that. You could still do this problem. Still need to go through the conditions. We're not really doing right and left-sided limits. Okay, we're just going to do the limit. And what do you know about the limit? It does not exist. Why? There's a vertical asymptote. There's unbounded behavior. Okay, if you didn't know how to graph this, what you could have done is actually plugged 2 in and said natural log of 2 minus 2, which is natural log of 0. Now you still need to know that natural log of 0 you can't do. So what I've written here in blue would be something you could have written. It's not something you had to write. Okay? Oh, I don't know why I'm writing condition number 2. If the limit doesn't exist, we stop right there and we say, therefore, f of x is not continuous at x equals 2. It's continuous for all the numbers greater than 2, but it is not continuous at x equals 2. Okay, so let's do number 5 the same way. Let's graph it, because it's kind of a different type of piecewise function, but then I'm going to talk about what you could do if graphing is not really your strong suit. So 1 over x, you may or may not remember, it's the parent function. It looks like this, with asymptotes on both axes. What is that minus 1 doing? Is it right 1 or down 1? Is it inside or outside the meaty part of the function? It's inside, right? So it's right 1. If the minus 1 had been out here, then it would be down 1. Okay, so let me draw that. So right 1. Here's the asymptote. Here's another asymptote on the x-axis, and it's just a sketch. And what this piecewise function is saying is for all the x's that are not 1, this is the graph we want. However, for that one time when x equals 1, for that single part of your domain, your y value is 2. Okay, and if this doesn't make your skin crawl, seeing that point on the vertical asymptote, I really don't know what will. The reason it's okay is because this is a piecewise function. For that one point in time, the asymptote doesn't count. All right, there's another example down here we're not going to get to today, but what it is this graph has a hole, and for that one hole, there's another point. And it could be filling up the hole, or it could be above or below it, and we're going to do that one next week. All right, so on with this problem. Condition number 1. What is the limit as x approaches 1? This is not, again, not really a left and right side problem. What is that limit? D and E. Same reason as before. Now, unlike the last example, condition 2 is met here. F of 1 is 2. But I don't even need to write that, because as soon as I get that the limit doesn't exist, then I can go ahead and write this. So it's really kind of like the best case scenario when the limit doesn't exist. I just realized I didn't write the word continuous. Anybody notice that? There you go. And that's an okay abbreviation for continuous. Okay, 6 and 7, we're going to do those next week. All right. However, I do want to do one more example. And it's not a proof. And I'll make sure you understand why. This does not say, is this function continuous? Why or why not? Explain. All it is saying is find the values where f of x is discontinuous. It does say sketch the graph. We're going to actually ignore that. We're going to do this analytically. So this would probably be a multiple choice question on the AP test, but even if it weren't, as long as you're showing your work, it's not a proof problem. You're not showing that this thing is continuous or discontinuous. You're just solving for x. So in a typical piecewise function, okay, you got a piece, you got another piece, you got another piece. Okay, this does not make this graph. All right, but what you want for continuity is for these things to line up, right, and connect. If they don't connect, then you get discontinuity. So that's what we're going to be looking for. So what is the x value when the first and second piece connect? What's the x value there? 0. So we are going to plug 0 into x here. We're going to plug 0 into x there. Not 1, because 1 is where the middle piece ends. That's going to come up in a minute. So I'm going to go 0 plus 1 equals e to the 0, and I'm going to put it like a question mark, because I don't really know that this is true. Is it true? Yes. Okay, so guess what? F of x is continuous at 0. And we didn't really show the full proof, but that again is not what they're asking here. So we have continuity there. All right, so that's not my answer. Okay, so let's try the next one. The middle piece is ending when x equals 1, and the third piece is beginning when x equals 1. So we're plugging in again, but we're plugging these other numbers in. So e to the 1, does that equal 2 minus 1? Does e equal 1? No. In fact, they don't equal each other. Therefore, we have not continuous at which x value? 1. I mean, technically, x equals 1 is my answer. The rest is just work. This was not a proof problem. If it came down to it and you just really weren't sure, you could do the proof. You could show all the steps here, okay? But this was just find the values of x, not show that it's continuous or not. Okay, I'm going to end there. Do you want me to